So I'm going to do a plane sweep in this direction from left to right. So this is my sweep line. And my sweep line and my event points are going to be these points. In order to do that, you sort your points on their x coordinates. And if they have equal x coordinates, you can take the one with the smallest, smaller y first. And you have a static event queue, which is going to, this sweep line is going to hop from one point to other point, going left to right. And during this, another important another important structure in a plane sweep algorithm is the status structure. During this plane sweep, what do we maintain? What does change? What is the thing that changes when we are doing this plane sweep? First of all, the status of this plane sweep is really dependent on the problem that you are trying to solve. Here we are trying to solve the closest pair. Now, if finding the minimum or maximum of things, what you usually do is you maintain a current minimum or a current maximum. If you are trying to find the maximum, this is what in general programming, this is what you do. You set it to a large number at first, and as you inspect your data, you update it with the current minimum you have found. And we are going to have something like that here as well. Let me call it h, the smallest distance I found up to now. I set it to for example, you can set it to the distance between your first two event points. If these are your first two event points, h may be initialized to this. Now, my idea is, while I'm moving on the sweep line, if the current h is this, my goal is, in order to make this O(n log n) time algorithm, your goal is to avoid testing all pairs of points. Okay, I mean, that obvious algorithm has O(n squared complexity, testing all pairs of points, and your goal is to avoid testing all pairs of points to guarantee an O(n log n) algorithm. You already spent n log n to sort these points on x coordinate, so you don't want to, and you are going to go over these points n times. You are going to go through these, and during these n times, you can at most afford the log n operation for each of these. When you come to an event point, at that event point, you can afford at most log n operations if you don't want to go more than n log n. Okay, because you are going to go through n points in your main loop. You have n event points, and at each event point, you can spend log n time. So now, when you come to an event point, that's a new point to you, and you want to inspect how far this point is to the other points. So if you inspect it with all the points that are already, I mean, imagine you are processing these points and all the processed points are put in a set, okay? So as you move along, what you can do is, when you come to a new event point, you can check its distance with all the points in the set, which is going to end up with O(n squared complexity, because if you have a set of m, it's going to be 1 point, 2 point, 3 point, at the end m points, it's going to be 1 plus 2 plus 3, it's going to be a series of to n, so it's going to be n squared operations at the end. So you don't want to compare this new point with everybody that you have processed before. But what you can do is a clever thing that we can filter out which points we test only the points which are potentially closer to us than the current minimum. So which points are they? For example, if currently I'm here, this is my new event point, I don't need to look at, and if this is h, okay, this was the current minimum, I don't need to inspect any point that has x coordinates smaller than if this was xe, any point that has less than xc minus h cannot be closer to this point. Okay, so this is, all the points here are guaranteed to be further from this point E. So any point within this window is potentially closer to me. But again, can this solution guarantee log n complexity? No. Why is that? Because imagine all the points are within this vertical window. I mean, you have all your points in this very small window. You arrange all of them. Their x coordinates may be very small, close to each other, but their y coordinates are different. So what you also need to do is, you don't need to, the same thing you did here, you can do the same thing here. You don't want to look for points which have, for example, smaller than ye minus h and greater than ye plus h. Okay, for these points which have y coordinates outside this range, they can also it's impossible to have a distance smaller than h to this point. So all I need to do is, when I'm doing my C-spline, all I need to do is look at this region. If there's a point within this region. If there's a point, for example, if there was a point here, it can potentially decrease the current minimum h. Now, how can you find these points that are within minus h plus h to your y coordinate in log n time? You need to have a binary search tree of the current points with respect to their y coordinates. Okay, if you have the current points, the points to the left of you, if you have them in a balanced binary search tree and with respect to their y coordinates, you can perform actually range queries in balanced binary search trees. So you can search for ye minus h. And if you have this as an array, for example, after locating this in log n time, you can find all the points within this range in linear time. Okay, so the trick is to have some kind of a data structure in order to access the points within this y coordinate range in log n time. Okay, if you do that, you'll be only inspecting very few points. And here you may argue, what happens, how many points can there be? If you analyze the geometrically actually, there cannot be many points within this window. Why? Because if there were, for example, if there were 2 points here within this upper rectangle, then h would be smaller, right? Since h is this, it means that if I put a point here, the other can be maybe here, but it cannot be, for example, here. It has since due to h, the points that are in this window cannot be close to each other. So you can only put, I think if you analyze it geometrically, you can at most put 6 points in that region. I think if you put these points here, like this, yeah, I think you can, so there are at most 6 points, actually, if you do not count this event point here. There are at most 5 points that you are going to test again. I mean, this is the at most case. If there's a point here which is potentially closer to E, it means that if there's a point here, I cannot have these points here, because since this is processed earlier, h would be smaller, okay? I cannot have this distance here. These distances here are smaller than h, which contradicts the definition of h, saying that h is the current minimum distance between the points. So after searching for this range, you are going to have an O1 number of points to test. So after spending this log n time, you are going to check the actual distance with very few number of points, and you are going to continue doing this. Now, one thing that you may need is, although you guarantee, even if you store all the points in your binary search tree, you still have log n search time, right? I mean, this log n includes all the points here. But for more efficiency, what you can do is, for those points who are before this, so this is my sweep line, and the sweep line has another brother sweep line, you can say, which is coming h distance before him. So what you can also do is, these points before this region here does not need to be in the study structure anymore. You can just throw away these points. They're never going to be, I mean, since their x coordinates are already h away from the current process point, I don't need to put them in my study structure. So what you can do is, as you move this sweep line, you can also, your q, so this is your event q, which is with respect to x coordinates, and you have a study structure 3, which is with respect to y coordinates. Okay, this is with respect to y coordinates. But what you can do is, you can, since they indicate the same points, in this event queue, while you are creating this study structure, you can have a link, a pointer to these nodes in the tree from the queue. So since these are points, the reason I'm having this pointer is that while I'm moving on this queue, if I determine that these 2 points are no longer needed, by following these pointers, I can locate the nodes in the tree and I can delete these nodes from the tree easily. Okay, you can delete such nodes from the tree, but again, as I said, this is not a requirement of, because even if you have all the points in the tree, you are going to still locate this y range in log n time. So at the end, after you process all the points, the final h is going to be the closest distance. Yes?
Hocam demin bahsettiğiniz fark o h'in daha küçük olabilme ihtimali. H her zaman zaten en yakın.
The current minimum.
H, yani öyle bir window olması çok realistik gelmedi. Çünkü sürekli değişen bir şeyden bahsediyoruz.
Exactly.
Yakın varsa daha fazla. Yani aslında orada bir range yok. Nokta var, bir de en yakın noktası var.
No, but yes, here the thing is this. When we come to, for example, we have processed everything up to now. The h may be something big, right? When we come to the next event point, we don't know, I mean, this event point is going, for example, this one is now within the window. Okay, I mean, this new event point may be closer to these other, I mean, it may have a much smaller distance. So there may be a point within this window with a smaller h distance, because this h is not computed based on the new event point yet. After we compute this distance, then we are going to reduce it. So sometimes there may be points inside. So this is what the closest point is going to be within that window, a closer point. So there may be, initially that may be very large. As you go on, there will be points. When you come to the new event point, there may be a point in that window. Any other comments? Okay, so, and the second question was about doubly connected edge lists. And the first part was, given the vertex and half edge records, find the faces, how many faces it contains, and asking, well, devise an algorithm to do this, finding the number of faces, just given the vertex and half edge records, and what is the time complexity of your algorithm. And this algorithm is very similar to the, actually you could have written it's in the book actually, the one which uses each boundary cycle as a node in a graph and finds the, and links to inner boundaries if an inner boundary is contained in an outside. So it links related inner and outer boundaries with some processing. I'm going to talk about it. And at the end, in this graph, each connected component represents a face. Okay, so this was the algorithm. But in the book, there are some parts that are not fully explained. For example, some practical problems. And even if you haven't mentioned those, I'm going to give you credit. But let's talk about, let's discuss the solution. Okay, we are given half-edge records. And means that these half-edge records have their also, first we need to assume that we can identify boundary cycles. Okay, if we cannot identify boundary cycles, we cannot find faces at all. So only the incident phase column of the half-edge record was missing, but from a half-edge, if we are given half-edge records, it means that their next and previous records are available. So what we do is, the algorithm is like this. First, we find the boundary cycles by going over we pick an edge, and we have a visited, unvisited flag for each edge, for example. We pick an unvisited edge, and by following its next pointers, we visit the other edges that bound the same face. The important thing here is that the next edge records, they are the edges that bound the same face. So we follow these next records until we come to the same edge. Okay, so this gives us a single boundary cycle. And we mark all the edges on this boundary cycle visited after this process. And we pick another unvisited edge, and we find another boundary cycle. Until there's no unvisited edges left, we continue finding these boundary cycles. So we have found ourselves, what we did, this process, what it does is, it partitions the edge records into groups, which are cycles bounding the same face. Now what we don't know is that whether these boundary cycles are inner or outer boundary cycles. And the technique in the book was just take a boundary cycle, find its leftmost vertex, and just check what kind of a turn this leftmost vertex is doing. And we do this for each boundary cycle. So after finding all the boundary cycles, we identify which ones are inner boundary, which ones are outer boundary. So we have done that as well. And now, this is the tricky part. For each one, now we have a graph, we have the nodes of our graph, but we need to put the edges in this graph. I mean, the nodes in the graph correspond to boundary cycles, and there are some of them are inner outer boundaries. Now, the trick is we need to relate, for example, two different inner boundaries, which are the holes in the same face, should be linked to each other. And also these inner boundaries, which are the holes of that face, should be linked to the outer boundary of that face. And the book says that the solution in the book was just find from an inner boundary, find the leftmost, go to left and find the first boundary cycle that it intersects with. And if it's another inner boundary, you put a link here. If it's an outer boundary, you put a link here and you stop going left at that point. Now, here, what will happen? So this is what we need to do. How are we going to find the boundary cycle? The problem is, given a boundary cycle, which boundary cycle is immediately left of it? What is the closest boundary cycle to the left of this boundary cycle? How can we find it? Since the solution does not ask you to find an efficient algorithm, just say what is the time complexity of your algorithm, you are free to do complex operations. Like what we can do is, after we find the leftmost edge, finding the leftmost vertex is after you find the leftmost vertex of this phase, you can construct a ray that goes left. So it's going to be, you can construct a half line that goes left from this vertex and intersect this half line with all the edges of all the other boundary cycles. So you do an intersection test of this because you don't have a data structure to find the closest one. So what you need to do is you need to check the intersection with all the other edges. And during this intersection, you may maintain the distance of the, if for example, if this half line intersects at this point, you maintain a distance, and at the end, you are going to see that there are two edges that intersect with this half line, which has the same minimum distance. These are the these are the two half edges, which are twins of each other, right? There are going to be, there's going to be a boundary here. So this half line intersects with this, and the distance d is going to be exactly the same for these two edges because they have the same and they have the same vertices. They are actually, these twin edges are on top of each other. Okay, the only difference between these twin edges are their direction. So this intersection point has the same thing. Now the problem is we know each of these twin, whether they are inner or outer boundaries, but now which one are we going to pick to connect to? In other words, when we are here in this edge, I'm going to have an outer boundary and inner boundary. Which of these links I'm going to put? Am I come to an outer boundary here, or is it another hole within the same face? Okay, so this is an important problem which was overlooked by the book actually. It says find the, because in the book we said that, I mean, these are, if it's an inner boundary, it appears to the left, to the right of the outer boundary. So there was some ordering in the pictures drawn in the book. But in real life, you are not going to have this order. These two edges intersect at the same point on the T. Now, how can we determine whether we have come to another inner hole, or it is an outer boundary of the, if it's an outer boundary here. So do you understand the problem? Or maybe you already know a solution which we can define it better. But my solution was, for each of these, for this boundary cycle, I mean, it cannot be both. First of all, these twin edges, actually, can it be? Since it's going to be an inner boundary and outer boundary, it's going to be the same cycle. These inner or maybe they can be even different cycles, right? The picture can be something like this. The twins. So I have to choose this one and link this as an outer boundary of this one. So I need to. So which one are you going to choose to link? Is what my solution is that, since I have the boundary cycles of each of these edges, I just check whether this vertex. So I do a vertex in polygon check. Okay, whether this vertex is in this polygon. If it's in this polygon, it means that it's the outer boundary of this inner hole. Otherwise, it's going to be another. And I also know that whether they are inner or outer boundaries, because I determined for each boundary cycle, I determine whether they are inner or outer boundaries by traversing they are either counterclockwise or clockwise. So if it's another inner boundary to the left of you, it means that you are two inner boundaries in the same face. You are two holes in the same face. And otherwise, if it's an outer boundary, it means that it's the outer boundary of this face. So I can find it by this inclusion check, whether this vertex is contained in this boundary cycle. So I have in my algorithm a test to check whether that a boundary cycle contains a point. So it's a point and polygon test is part of the algorithm. And after you do that, after you draw the correct edge, you do this for each boundary cycle, by the way, and then you have a complete graph. Not a complete graph. I mean, what the process is completed. You have a graph which shows the boundary cycles and their relations between them, and then you do a depth first search in this. Any traversal is going to do fine. You again, similar to what you do boundary cycles, you start with an arbitrary node here. You follow the links. You find the connected component in this graph, and this connected component is one face. You pick another unvisited node. You find another connected component, and at the end, the number of connected components in this graph is going to be the number of faces. Yes. Yes, yeah, the number of faces. Yeah, that's also very much clever. Yes. So you don't need to actually. Yeah, that's actually you should. That's a full credit answer. So you don't need to do. I mean, I wish you have interrupted me earlier with this complicated example. Yeah. So yeah, each outer boundary is. Yeah, that's a very is identified by a face. So just after you find whether they are inner or outer boundaries, the number of outer boundaries in this graph is the number of faces. Okay. And the last thing I'm going to discuss is draw an example doubly connected edgeless for which this is false twin. Twin is different from. I think most of you have done this. You can just an example like this is an example in which you can pick, for example, here. So this is the outer boundary of this. Okay, so it's counterclockwise. And now I'm going to do this. Okay, and this one is a hole. So if you do something like this, the next of this one is this. However, it's twin. I think you should pick something else, but you can find an example. So I'm not going to go over the detailed solution of this, but there's an example in which it's possible to find an example in which the next of an edge is different from its twins previous twins. Okay. Mm-hmm. Yeah, I think if you pick something here, it's going to work out right. But the thing I'm going to, you need to be careful here is that you cannot use these previous and next edges arbitrarily. These are defined uniquely, okay? And next and previous and twin, they are all uniquely identified. The next, they have to, when you are going next and when you are going previous, they have to bound the same face. By, for example, the previous of this is so this is this is clockwise. So the previous of this is going to be which face this is bounding to the left. So it's the hole here. Okay. The previous of this is going to be this one. Okay, it's not this one. So the previous of this is this. Because it's the clockwise inner hole which is bounding this face, and this face's inner hole is this. So each of these previous and next are defined uniquely, and in your example you need to be careful when defining these next and previous edges. Okay, so that's it for homework solutions. Let's have a 10-minute break, and I'm going